Previously, we have defined mod 2 degree of a map between two manifolds of the same dimension. We also made a lot of fuss about it, but I promise you that wasn't all hype. We're gonna do some fun stuff now. We're gonna use this mod 2 degree to talk about existence of zeros. So how could mod 2 degree tell us anything about existence of zeros? How could it help us tell whether or not f has any zero in M? Well, there are two ideas here that we want to use. First, we want to rephrase this condition, that f has a zero in M. Well, if we have some kind of norm on N, then one way to rephrase this is to realize that f has a zero in M if and only if this quotient of f by its norm is a well-defined function on M. Or we can put it slightly differently. If f is not constantly zero on M, then on the subset of M where f does not vanish, this quotient is actually a well-defined map. In that case, observe that f has a zero in M if and only if this map actually extends to a map on M. Thus now we have turned the question about existence of zero into a question about existence of extension of map. Now, mod 2 degree is just defined as intersection number, and we do have a theorem about intersection number and extension of map. Remember the boundary extension theorem. Recall that this theorem says that suppose we have a map G on the boundary of some manifold M. If this map extends to the whole of M, then the intersection number mod 2 of this G with any closed submanifold of this codomain of complementary dimension must be 0. Alright, so now let's rephrase this in terms of mod 2 degree. Let's fix our setup as before, where M and N are manifolds of the same dimension, M is compact and N is connected, so that we do indeed have the notion of mod 2 degree. Now let's suppose that we have a map F from the boundary of M to N. Then the boundary extension theorem says that if we could extend this map to a smooth map here from the whole of M to N, then the degree mod 2 of F must be 0. Actually, let's phrase it slightly differently because we want to use the contrapositive of this. So, let phi be a map on the boundary of M from the boundary of M to N. Now, suppose that the degree mod 2 of phi is not 0. Then the claim is that phi cannot extend to the whole of M. Thus, there's no way to complete this to a commutative triangle. Alright, so now we want to use these two ideas that we just discussed to build our first baby theorem about existence of zero. Since in this idea we need some kind of norm, let us take for example some function f from C to C. Here we're viewing C as two-dimensional real manifolds. And let M be a compact submanifold of C with boundary. Right now, let's suppose that f has no zero on the boundary of M. From our previous discussion, we see that that means that this quotient is a well-defined map on the boundary of M. Actually, since it has norm 1, we can view it as a map to S1. Now the claim is that if the degree of this map, if the degree mod 2 of this map is not 0, then f must have a 0 inside M. Alright, so let's see why. Now, from this discussion here, we know that degree of this map being non-zero implies that we do not have an extension. There is no map here completing this commutative triangle. But then, as we have mentioned before, this means that f must have some 0 in M, because if f doesn't have any 0, then naturally this is a map on M. So see, for a few seemingly very simple idea, we got a very cute theorem. Isn't it incredible that just from information on the boundary, we can tell whether or not f has 0 inside of M? You'll see that kind of phenomenon again in complex analysis, and actually we'll discuss another approach to this using complex analysis. but that should be in the complex analysis playlist. Next up, we are gonna steal a teeny bit more spotlight from complex analysis. We are gonna prove one half of the fundamental theorem of algebra.